Wonderful. All right. So welcome everyone to another OCP Tap session. This is call number 92, and I'm talking to you guys from Cider. So I joined Cider this year. So our speaker today is Greg Armstrong. So Greg Armstrong has been working in the telecommunication industry for 29 years as a system architect and application engineer, as well as embedded system engineer. As a principal system architect, he is responsible for the technical definition of new timing products, both silicon and software, and development of products roadmaps with the timing products division at Renesas Electronics. And he also represents Renesas in IEEE 1588 and 3335 working groups as key contributor to CableLabs Synchronization Techniques for DOCSIS Technology Specification for Mobile Backhauls. With over 18 years of synchronization experience, Greg's expertise is in technologies that enable the transfer of frequency, phase, and time synchronization over packet network, such as SYNC-E, IEEE 1588, and TP, TOP, RTP, and CSO, PSN. I don't want to lie, I probably don't know half of them. He also has a background in Ethernet IP switching and 10 gigabit SDH SONET Ethernet framer mapper. Greg has been advising system architects and system engineers at industry-leading companies on network synchronization for many years. Also, he has presented papers at various conferences and has patents related to clocking. Since 2016, he has been providing a tutorial on phase lock loops and PLLs and ORAN Foundation at both International Timing and Sync Forum ITSF, and the workshop on synchronization and timing systems WSTS conference. And today's talk is simply about servos, not the motor servos, the clock servos. And with no further ado, Greg, the floor is yours.
All right, great. Thank you, Ahmad. Thank you to the OCP TAP community for inviting me to talk today. So today, my talk is going to be a lot about synchronization and primarily introducing servos, in related to not a motorized, but it's still a servo mechanism used for clocking. We'll talk about how that interacts with protocols such as the precision time protocol and things like that. We all here, I'm sure, understand the importance of synchronization, but sometimes I don't know if we all fully understand what is synchronization and what are all the building blocks involved with that. This is a figure I use a lot in a lot of my presentations just to give a summary of, what is time, phase, and frequency, because sometimes we don't really understand the differences. There's a relationship to all of them. Frequency itself, fundamentally is really a statistical term. It basically represents how many events happen per second, usually in a unit of hertz. So for clocking, it would be how many rising edges occur in a second. So we talk about 10 megahertz clocks, or 1 hertz clocks, or 156.25 megahertz clocks. And so those are just typically representing how often that clock edge repeats itself within a second. The phase is actually, it's actually itself an angular rotation vector, but in clock terms, you can look at it as, it's really just the time related to, oh, look at that, mind of its own. It's a time related to the period of a repetitive signal. If you looked at each one of those edges, it would be, what is the actual time unit between those edges? Typically we a lot of times we read it as a period. So we talk about it as nanoseconds or some unit of time. And that gets us to time. What is time? Well, typically units of second. And really, you can look at it as time itself is really just a label. It's a label onto that repetitive event. to try to say, well, this is when it occurred with some reference to an absolute source, such as time, like a startup time, and things like that. So for synchronization, you know, from a standpoint of clocking, we really look at, there's two things that we try to synchronize. One is frequency. So this would be looking at the repeated edge of a clock, and we're trying to repeat a signal either at the same frequency or maybe a multiple of that frequency, but we want it to occur at relatively the same time. And so that's a frequency synchronization. We want that frequency and the phase relationship to be repeatable. But the one thing with the frequency component is because it's a multi edges, let's say megahertz, when you're looking between two signals, it's hard to say, well, which edge should be my starting edge for start of measurement in relationship to another edge. And so that's where phase and time comes in, where typically they're identifying a lot of times a lower rate type interval, you know, like a framing interval is used commonly in telecom, like a 8 kilohertz signal. When we look at, you know, multi types of frequencies, we might even divide that down even further to like a 1 hertz signal, or some people refer to as a pulse per second. And then again, time is just putting a label onto that. So a pulse per second happens every second, but you want to have some starting point of that counter to be at your what we call epoch time or time zero to say, well, how long has it been since the first time count started? So if we look at it in terms of like, you know, relating it to a graph or relating it to clocks, you can look at it as simply as, you know, if we have no synchronization between two clocks, well, we could have two sources of clocks, let's say oscillators or crystals that are, you know, fundamentally everyone looks at it and says, oh, it's the 125 megahertz clock. But, you know, so that it's roughly how often it will cycle itself in a second, but there's always some sort of error. Just because of the mechanics of the crystal, there's going to be a bit of error relationship to maybe a very ultra stable clock like a cesium, rubidium. And there's been lots of talks about clock sources and things like that, so I won't get into that. But because of that relationship to them, if you looked at it from a standpoint, is if you just took that clock and fed it right into a counter, they would start incrementing at relatively the same pace, but over time, one of them might be a little bit faster in incrementing or slower in incrementing relative to another clock, even though they both approximately are 125 megahertz. So with frequency synchronization, what we're trying to do is say, well, how can we get it so that those clocks actually increment at about the same pace? Now, it doesn't necessarily mean that the counters start at the same time. So one could have started at 0, one could have started at 1,000. But if at the next edge interval of that clock, you would see a common relationship. And that's what we call frequency synchronization. And some people refer that as being syntonized in terms of the frequency component. But again, because there's no relationship of the counter, although you're, you know, if you took a sample time and measured it in relationship to that clock, they would look like they're synchronous. But if you went over time and then started the measurement again, it comes back to well, which edge should I start measuring from? And so that's where phase synchronization comes, and even time synchronization, where we actually try to have the events have a common relationship to a source. So for phase, a lot of times it would be some sort of framing signal, like an 8 kilohertz signal or even a 1 PPS. And that would indicate when should we have the counts incrementing and all starting at the same time. So if a system powers up, they would go out and say, hey, where should I start my counter? I shouldn't start at 0 because that's not the epoch time of when time has started or when we want to make our relationship to. And so that's called phase and time synchronization. So frequency synchronization, you know, much as the term says, it's looking purely at the clock. You know, and if you're looking at it from multi clock signals, if you divided those clocks to, let's say, a common frequency, and I mentioned like 8 kilohertz or even 1 pulse per second, if you divided those the clocks down to that common frequency and looked at the relationship of edges of that common clock, you would see a phase offset between them, but it would be a static phase offset. And if you see that static phase offset maintain a common denominator of that, where if you divide it by a common denominator and that denominator stays static, then we call that being frequency synchronized. If that denominator maybe is only bounded, so sometimes it may vary over time. There is a term, it calls it plesiosynchronous. It's a term that was used in telecom a long time ago. Generally, most systems now move more towards a synchronous standpoint where there's a common source that you can make your measurement to, either a common frequency source or a common time source that is coming from that. And if you look at the differences between that, there's typically would be some sort of phase offset. And if you can get that phase offset to be static or close to zero, that is when you establish what people will call phase locked. But phase locked doesn't mean phase synchronous. It just means the phase relationship is locked, which implies that the frequencies are synchronized. And there's many examples of how this works. I threw up an example here looking at just simple physical layer clock distribution, very common in SONET, SDH, and even now Ethernet-based systems, is a lot of times a signal will come in representing data. There'll be some sort of modulation of that signal, but you could use a clock data recovery circuit to recover a fundamental clock from that, and then that clock could then be used to measure some sort of time interval, and then you could resynthesize that clock in relationship to that and allow the synchronization to kind of daisy chain amongst different nodes. And, again, typically the clock would come in, and now you kind of represent more of a nice digital circuit. A lot of people look at it as like a square circuit of representing the clock, but that could then in turn be used to drive another transmitter to modulate data onto that and send it over a signal. And so in synchronous networks like SONET and SDH, that would aid in part of the synchronization protocol itself. For Ethernet, the importance of the synchronization of the physical layer isn't as important. And so a lot of times there was no real relationship between the recovered clock and the retransmitting clock. The transmitter usually just used its local clock and recovered the local clock using, to basically clock the data in, but it would re-clock the data out with its local clock. And so by synchronizing those, you could actually get more of a known relationship between the receiving side and the transmitting side. And, in telecom, we called that synchronous Ethernet, which maybe not a greatest name because we weren't really synchronizing Ethernet itself, but it was synchronizing the physical layer in terms of that you could actually now distribute a frequency signal throughout a network and recover it at different nodes that needed to have some traceability of that clock. So, one of the challenges, though, when you start doing physical distribution is, although you're trying to find what we would call the significant events, they never will occur exactly at the same time because there's always something that's going to have some influence to it. Going over physical layer, if you're going over long distances, the signal over time, over distance will get attenuated. So you won't get like a nice, fast rising edge. There might be variations on that edge. And even other external environmental components like temperature and other things can influence how fast those edges rise or fall over time. So, what you're trying to do is you're trying to identify at least where those significant events are, and then try to maintain a relatively small time interval error between those events. And a lot of times that's where it comes into the concepts of a servo, which I'll get into later. But even with packet-based frequency distribution, it's still looking at the concept of significant events. The difference is instead of looking at it from like a rising edge of a physical clock or a physical signal that may be used to send the data, we're looking at maybe either the transmission time of when the event occurred or even the reception time of when that event was received at the other end. And so a lot of times techniques would be used to try to recover frequency components from this, even though it's not coming over a physical layer clock. Now, although, conceptually it sounds simple to say, well, it's very easy to see when those events occurred. One of the difficulties of that type of distribution is going over networks that may not be fully participating in that distribution of the network. You can get delays of those packets as they go through the system. And those delays can impact the difficulty of trying to recover that clock. And so a lot of times we see people implementing what we call adaptive clock recovery techniques to try to recover that clock, where you'd have to look at the packet flow itself, and again, look for those, try to identify those significant events, but try to effectively filter out any of the variation that may be occurring of when those significant events are arriving at the receiver. And and then again, a lot of industry standard organizations looked at this and tried to identify ways to help define how can you recover these clocks when they're coming over certain networks, or maybe identify ways of defining how many hops should that go over before you kind of have to say, look, I need to try to recover this clock and maybe redistribute it down this downstreams, because if it goes over too many nodes, it just becomes too difficult to try to recover. And so, some organizations like the ITUT would come up with ways of saying, well, let's try to model a network, model some delay variations of that model so that we could test different algorithms that are trying to recover that to say how well can they redo it. And so that kind of is how some of these little profiles came about to try to measure it. But the reality is if you look at the reality, is no networks behave like a nice statistical algorithm or model that you try to do. And so the reality is you needed a very advanced type of timing recovery. And so people would develop algorithms to try to do it, different techniques to try to do it. You could look at trying to identify the mean, which works well over some mediums of distribution. But for a lot of times wire-based distribution, it actually, you found what happened is some packets actually get very lucky and get through the network fairly quickly, and other packets don't, and they get delayed at different intervals. And depending on how busy a network is, that even can influence some of those lucky packets that, although they're lucky, they're not as lucky to get through as fast as possible. And so it made for very difficult and advanced algorithms to be developed to try to recover clocks over those type of networks. But again, for something like just trying to identify a frequency component, they were useful in trying to recover the frequency. But as I'll get into later, what really became difficult was trying to recover aspects of phase and time from that, because those changes of packet delay variation and even the changing of the delay of the lucky packets of sometimes being very fast, might be at periodic times being slowed down, and upstream and downstream could behave differently. It makes it very difficult using aspects of protocols like two-way protocols to try to recover the delay from those packets. So that kind of leads into time synchronization. And again, all time synchronization is basically, a lot of times it's adding on top of the frequency a component of a phase and a time of day. And so a lot of times the fundamental signals you see representing this is a 1 pulse per second to represent the phase, and a time of day just being a serial stream representing seconds and sometimes even nanoseconds of that clock. But again, if you're using something like a 1 pulse per second, really the only important data that you need to come from a time of day is the seconds. Because from the 1 pulse per second, hopefully you could use that to try to synthesize a frequency component to represent maybe the sub or nanosecond representation of that signal. But again, that can be difficult. One of the more difficult things to do is trying to synthesize high frequency clocks when you only get a reference point every second. So as you can appreciate, if I was trying to synthesize a 1 gigahertz clock where I can guarantee I get 1 billion events precisely in a second, it can be very difficult because you can only measure how well you're doing every second. And so it can become difficult to do that. And so typically, a lot of people don't use 1 PPS as a distribution means. You usually use other mechanisms to distribute phase and time, such as protocols, which will use a frequency component to try to get that sub-nanosecond component, and also try to maybe deliver that timing information more than once a second, or have something else that can help stabilize the clock so that even if you're only getting an update once a second, it makes it easier to try to recover the frequency component and get that precision in how many events you can make sure happen exactly within that 1 second. And so, that's where a lot of this time distribution protocols come from. It was just because the reality is looking at just trying to distribute a 1 PPS and TOD, although conceptually very simple, you could just use a simple coax cable to try to do that. It became very difficult to try to use that as a signal to synthesize or regenerate frequency components out of that. And so a lot of times it was much easier to look at protocol-based mechanisms. And the other advantage of protocol-based mechanisms is you could use concepts like two-way time transfer to try to measure delays as that protocol is going over the network. And that's effectively what comes into synchronization protocols. And stay with me, eventually we will talk about servos. So two-way time protocols, I won't get into a lot of details here. Again, a lot of presentations by the OCP TAP community about how these work. But basically the basics of it is, some time transmitter will send information downstream to say, hey, this packet left my node at this time. The downstream nodes would receive it. They would timestamp saying, well, this is when I received it. And then they would maybe send a packet back to say, hey, by the way, I'm going to send you a timing packet. This is when I sent it using my local time. And then the receiving end or the far end would receive it and send, well, this is when I received that, and send that back to the receiver. And once the time receiver gets all this information, it can do a lot of calculations. It can calculate the offset of its own clock in relationship to the time clock. And again, that's just a measurement offset. So it'll just tell you what your error was, but it doesn't tell you how do you improve it. And it will also tell you about the delay, which is important because the delay tells you, well, how long did it take for you to get that time to me? Because I want to account for that when I try to get my clock to be the same as your clock. Because if I don't know that delay, then I'm always going to be late in relationship to it. And an analogy a lot of people use is like, it'd be like me looking at my watch, writing down the time on a piece of paper and mailing it to you, you getting it. You'll know I could tell you very precisely when I sent it, but it doesn't have a lot of meaning to you if you don't know how long it took to get to you. You don't know how to measure that. And so these are the benefits of the two-way time protocols that allows you to try to deliver time and also measure the time it takes to get that delivery to the receiver. So the precision time protocol was just a means to try to identify a way to implement a two-way protocol, which again wasn't uncommon. There is NTP is a two-way time protocol. There's many different two-way time protocols. But what the 1588 standard tried to identify was saying, in order to get the accuracies of the two-way time protocol, we have to maybe look at trying to get assistance from the hardware that is sending the timing. And so they introduced the idea of what if we introduce the time stamping function of when something was sent or received. If we introduce it closer to the physical layer, then we can start getting more precision in the terms of the accuracy of when something arrived and when something was transmitted. But again, if you look at it from a standpoint and read the abstract of the 1588 protocol, it says a lot of words there are used that we have to be aware of. One is it says it supports synchronization accuracy, and it says time transfer accuracy can be achieved if a properly designed network. So these are the things that we have to be aware of, that just because we read the standard, just because we implement the protocol, it does not guarantee synchronization, nor does it guarantee accuracy. So there's aspects of that that have to be built in. And I put a picture here that's probably not uncommon. You probably have seen this about how do we look at stability versus accuracy. And it's what I put there was kind of examples, right? So if we look at something where, what if I measure something, I'm seeing it's very stable, but it just may not be accurate, which means it just doesn't know where its reference is. But it is able to maybe clock something very accurately. And that could be an example of like these high stability oscillators. You hear about high stability TCXOs or high stability OCXOs. that if you measure the variation of that clock over time, it's very stable. You get a very stable error, and that error is bounded so that you almost get like a flat line when you look at it from a phase and time relationship. But it's not very accurate because there's no label to it. It's just a clock, right? You don't know when did it start. You're not counting anti-counter is being driven by it, things like that. And if you're not stable or not accurate, then it's kind of like, looking at it, well, what if you just threw down an uncompensated crystal or MEMS device that is just basically oscillating, but it's just oscillating with no sort of corrections, right? There's nothing to try to improve its accuracy. And again, it has no notion of where it should be. So, from a standpoint of us, we call it as a drift, right? It's just all of a sudden is drifting at some relationship. But even if you look at the drifting aspect of it, it's kind of can be random, right? It might look like it's drifting in one direction, but all of a sudden it goes in a different direction with no apparent reason, right? So that becomes like not stable, not accurate. And then you can get aspects of, well, I can get very precise measurement, right? So again, I could use PTP and precisely tell you exactly when you transmitted and exactly when you left in accuracies of nano, even sub-nanoseconds, but it may not be very stable. Because what if I'm using one of those like uncompensated oscillators to try to stabilize the clock? Well, it's always going to be drifting on me every time I recorrect it. And so it comes to, well, how do you get stable and accurate? And that's where we introduce the concept of servos, right? This is where something is sitting there using the measurement information and using the aspects of maybe the local clock stability and combining that information to try to get very stable and accurate relationship of a clock. And so that is what the value of 1588 is, right? It allows you to build these networks, to distribute the clock. It tells you mechanisms of how to establish a communication channel. And it also talks about a lot of times how to get the precision in the timestamper by pushing that closer to the physical layer to get those accuracies. But the key thing to take out of this is, although it allows you to, it basically says that it's a protocol that you must still synchronize its local clock to the GM. So it says you must synchronize, but then you go and read the standard, it says, but this is outside the scope of the standard. And sometimes even profiles written for the protocol won't even say, well, how do I do this? How do I do this? What is the servo? And so, a lot of times I say, and I put the slide up again, I repeat, 1588 is a protocol. It itself is not synchronization. You can't just take the protocol and magically think your systems are synchronized. There's a component missing, and that component is the servo, which is really getting into our talk. So again, you have to just be aware of this. I highlighted things right out of the 1588 standard. But the key is don't be afraid of this. The nice thing about this is some people have gone off and implemented servos for us to use. And there's also examples of hardware-based servos that can actually allow you to get even more precision and accuracies in your clock synthesis and distribution of that clock. And that's what we'll talk about, phase lock loops and other things that could be used to aid that. And again, and like I said, I think the reason a lot of us aren't aware of servos is some people that have implemented 1588 stacks have kind of hidden this from this, right? And an example is Linux PTP, a very good example of an open source stack that someone wrote that represents the standard. It's compliant. It implements a lot of the core features, a lot of the optional features. A lot of profiles have been developed and uses it. And it looks very simplistic. But it itself, there's a little servo in there. Someone wrote a simple little PI filter and even an example of using a weighted mechanism of filtering and says, hey, well, I can filter this clock offset that's being sent to me and resynthesize the clock to try to eliminate the drift component and try to maintain that traceability to the grandmaster clock. But again, a lot of people wouldn't know how to configure it, use it, or even be able to understand it if they try to read that code. And so that will get into, well, how can I go about and get maybe some of these aspects in terms of more simplistic mechanism. So, I'm going to talk about a phase lock loop. And again, we said at the beginning, this isn't, we talk about servos and it's not about like a servo engine. But really, all a servo is really trying to talk about it's just a control system that generates a signal and uses a feedback mechanism to be able to measure how well are you maintaining your signal to the input, right? So again, a lot of people use cars as an analogy, right? If I go and look at the highway sign, it says I can drive 100 kilometers an hour. I look at my speedometer, it says I'm driving 90. Well, I step on the accelerator until I get it to 100. And once I get it to 100, I'll ease off on the accelerator. If I go, above 100, I'll ease off. It's same like that, right? So it's basically you are acting as this feedback mechanism. You're looking at the speed limit and you're looking at your speedometer and you're trying to adjust the speed of your engine to maintain that. So all a phase lock loop is doing much the same thing. But it's now just converting it using a clock is the input, right? So a clock, as we highlighted, has events that are occurring. That's the rising edge, and they occur at a very statistical interval. It could be a 25 megahertz clock, a 156.25 megahertz clock. Any type of clock is coming in, and what you're doing is you're trying to measure the phase relationship of that clock back to a feedback mechanism, so of your output. So you're trying to basically clock some sort of oscillated circuit. So some circuit is oscillating at some rate as well, and it could be a same rate as the input. It could be a different rate of the input, but maybe a common divider. And you're trying to use that mechanisms to try to control to either speed up or slow down the clock. And the component that's in between all that is there's certain aspects where, well, you could either react very quickly. So if I detect my speed is very slow, I could slam on the accelerator to try to speed up. And then as soon as I detect that I've hit it, immediately take my foot off, right? Or I could speed up, and if I detect I'm going too fast, I could slam on the brake, right? Well, that's not going to be a very pleasant drive, right? If you're sitting in a car, you're going to be jerked around, and it's not going to be pleasant. So typically what you try to use is some sort of mechanism to try to, make a more of a gradual increase and gradual decrease of that. And depending on certain conditions, you basically eventually try to stabilize things so that you kind of have a nice equilibrium of saying, well, yeah, I now see I'm driving at the exact speed I want. I'm going exactly 100 kilometers per hour, kind of like a cruise control, right? I've now set it, and once it detects it thinks it's going there, it's just going to sit there and keep doing it, right? If the local oscillator speeds up a bit, kind of like me going down a hill, it will try to ease off to try to slow it down. If I start going up a hill, or my clock tries to start slowing down a bit, my local clock, it will try to speed up that circuit to try to keep that 100 kilometers per hour. So it's a very similar concept, and why a lot of times you hear servos being used in clocking, because it's a very similar mechanism. So I'm not going to spend a lot of time going through the next few slides. There are a little bit more details of each component of the block. So I'll highlight some of the key capabilities, mainly just to introduce, hopefully you're going to start seeing how precision protocols kind of fit into a concept of a phase lock loop. So the first main building block of a phase lock loop is the phase comparator. You'll hear different terms. You may call it a phase detector, phase comparator, phase frequency detector. Effectively, what it's doing is it's looking at some sort of input reference, and it's looking at a feedback, and it's just measuring the error between it. Very similar to like a protocol that is snapshotting when did I transmit and when did you arrive, right? It's a very similar kind of concept. And so it's just timestamping those two events, and you're effectively send that error off to the loop filter. And there's many different ways you can implement a phase comparator. And a lot of today's digital phase lock loops, a lot of times what they do is they use what they call a time to digital converter, where they'll use some sampling clock that will sample the edge of when it arrived, and then it'll sample the other edge when it arrived. And those two counters will just be used to determine a raw offset, and a digital word will be sent to the loop filter to say, hey, you're off by 10 nanoseconds. And then every edge will be measured. So one of the advantages of the phase detector is it's a continuous measurement, right? So you don't get any missed cycles. Every edge event of the input will get measured to every edge event of the feedback. And so you get this continuously coming to the loop filter. And then the loop filter will take that information and it effectively applies what we call a loop filter. A good way to look at a loop filter is it's just almost like it's just a big averager, right? It basically says, well, give me a bunch of information. I'll try to average it over a long period of time, and then I'll try to spit out that average to some sort of control circuit to control the clock itself. But, you may want to do averages over a very short period of time, or you may want to do averages over a long period of time. And from our standpoint, what we call that is a bandwidth. It's basically saying, how long do I want to wait in my time interval to average out these phase information that's coming in? So if I have a very wide bandwidth, like let's say 1 kilohertz bandwidth, effectively it's saying I want a very tiny window. So I may only take about 4 samples, average it out, and immediately spit off an offset. So as you can appreciate, that would be a very fast reactor to any changes in phase. So if that phase changed at all, like all of a sudden 10 nanoseconds occurred, that 10 is going to spit out fairly quickly coming out of the loop filter. But if I want to open up my window and say, well, let's average over a very long component of time, then that's like almost lowering your bandwidth to maybe like, let's say 1 hertz or maybe 1 millihertz. We were saying, I want to have a very long window of measurement, and over that very long window, I'll output the average to the control circuit. So there you might have, well, what if there's like a lot of variation of noise, what we a lot of times call jitter, where maybe it's like 10, then 15, then -5, then 0. Well, all that numbers will get fed into the loop filter, but averaged out, right? And then over a time period, it may just spit out a 1 coming out to the controller and say, hey, there's a lot of noise out there, but the reality is on average, you're only off by about 1 nanosecond. So correct your clock 1 nanosecond and you'll be okay. And so this is basically what the job of the loop filter is. And there's many different ways you can implement that. I'll talk about a couple of them that's commonly used, and mainly because it's just a simple what we call a two-pole filter, and it allows for a very simplistic generation of a clock and also averaging of the clock in terms of being able to maintain concepts of holdover and things like that I'll talk about. And then finally, that control signal comes to what we call some sort of controlled oscillator. There's, again, different ways to implement it. It could be a voltage controlled oscillator where you're using voltage to try to speed up or slow down. A lot of circuits today are used as what we call it digitally or numerically controlled oscillators, where they use basically changing of the numeric dividers or some sort of frequency control component and try to speed up or slow down, or called a frequency puller, where you take a free running oscillator, your local clock, and just try to speed it up or slow it down in order to resynthesize the clock. And then you would feed that back through the feedback circuit back to the phase detector. And so that's how you get your closed loop. And so it basically comes up, you have your phase detector, your loop filter, your steerer, and then it feeds back to the phase detector, and that's how you get your closed loop and you get your feedback mechanism in place. And again, as I highlighted, that digitally controlled oscillator doesn't necessarily have to run at the exact same frequency of your input. Like if it's a 25 meg, it doesn't need to be a 25 meg clock. A lot of times that VCO is running at a much higher frequency because it's trying to synthesize other clock frequencies from that source. And a lot of times they're much higher. Some VCOs run at gigahertz, like 15 gigahertz. So as you can imagine, when this closed loop is stable and running, it means that it guarantees 15 billion clock cycles exactly in between each input if that was a 1 PPS input coming in. So it's a very useful mechanism to try to stabilize the clock and get that stability. And then if that clock is coming from a source that is very accurate, you get the accuracy as well. So you get both components of that using a servo. So as I mentioned earlier, there's different ways of implementing a loop filter, but one of the most common ones is what we call a type 2 DPLL, which is effectively meaning it uses a second order filter. And when you hear that, all it means is there's what we call a proportional term. And all the proportional term is it's just basically the absolute difference of the error, right? So if the phase detector is coming in and says your error is 10, then the proportional term is just 10. That's what's going to come in. The integrator, what it does is it basically takes that 10 and it basically says, well, I'm going to do a very long-term average of that 10. And so if I continuously get 10, eventually I'm going to spit out 10 to the summator there, which means it gets summed to the proportional, and then that's the final value. And so this is how you get where you see a very quick offset. And I apologize, maybe I'll turn on my pointer here. That's where you get where the proportional term, when it first sees a phase offset, will immediately start changing the phase of your clock. But over time, the integrator basically starts catching up to that. And as the integrator gets closer and closer, well, the proportional term becomes smaller and smaller. And eventually you kind of slow down and stabilize. You might get a bit of an overshoot, undershoot, but eventually you kind of stabilize to where the phase you want to be when you're doing that clock. So the nice advantage of a type 2 PLL or a second order filter is it means that the relationship of the input edge to the output edge is basically stabilizes to get a 0 phase offset. And so, and the reason it can do that is the integrator basically determines the frequency difference between the local clock and the clock you're trying to lock to. And so because that basically is representing the error of the local clock to your high stability frequency clock coming in. And so over time, the integrator is going to represent that over a long-term average. So your proportional term starts stabilizing where hopefully it's getting closer to 0. And that's where it's going to settle to, is a 0 offset to the input. And so it makes for a very easy way of seeing relationships, input to output, and also be able to generate any clock and have that common relationship between edge to edge alignment, which means you could have integer relationships. You could even have fractional relationships to that clock. But if you go down to a fundamental common frequency, they would have a common edge alignment traceability over time, like a 1 PPS or 8 kilohertz. But the other component they have to be aware of is one thing that the integrator allows us to do is control how fast we react to changes of the clock. And it's what a lot of times people talk about is like a gain peaking, which means if there happens to be a lot of noise very close to where we're trying to kind of cut off or average out the error, if you don't have an integrator, if your integrator is kind of too quick, you get kind of a peaking. And that peaking can actually be very devastating in networks that you're trying to distribute a clock, because you're basically adding a noise component and it's basically a gaining of that noise throughout your network. So if you have like 20 nodes that are all introducing this gain, you're going to have a very bad clock traceability back to your fundamental source. So a lot of times the integrator is there to try to manage that gain peaking by keeping it very small, typically down to like 0.2 to 0.1 dB type of noise gain peaking that you want to see there. And so that's the advantages of the integrator, is it allows you to not only control how quickly you respond, but over time it gets a nice average of your traceability to the clock, that it represents the exact error of your local clock to the clock source that you're locking to, which becomes important when we start talking about holdover. Now you might ask, well, why am I talking about PLLs? Because I'm showing physical clocks coming in and physical clocks coming out. But that's not to say that PLLs can't be used for packet-based clocks as well. And it's very commonly used for packet-based clocks, especially when you look at doing phase and time clock distribution over networks and using it for applications like telecom, where you need to resynthesize clocks like RF clocks for radio units. And these are being synthesized in like gigahertz or even tens of gigahertz. You can't synthesize this using some sort of simple FPGA or digital circuit to try to synthesize a digital clock rising and falling 10 billion times a second with very precise, clean edges coming in out of that clock. So PLLs are very commonly used still, even with packet-based clock distributions. But as you can appreciate, all that's kind of taken away when you go from a physical layer clock to a packet layer clock is you just basically, the packet layer clock uses a measurement mechanisms like PTP to measure the offset between the grandmaster and the local clock. Well, that offset is affected like a phase detector offset that would come from a phase detector of a physical clock detection. So you could just feed that into a simple loop and still get all the same characteristics, of the low pass filter. And then you steer your local oscillator to represent that clock. And the feedback mechanism there is effectively your local timestamper, is effectively your feedback. And then the protocol runs again and makes that measurement. And again, the idea there is you're trying to get that offset from master to converge to 0, so that you know that your local clock is now synchronized precisely to your grandmaster clock. And the other advantages that PLLs allow you is there's other modes of operation that you don't commonly get if you're just looking at a very simplistic clock circuit. And the main one is the concept of holdover, which we'll get into as well. But the idea of holdover is it's almost like a memory of saying, I'm going to try to remember about on average where my offset is of the local clock to the primary clock, so that if I lose that reference, I can use that as a starting point to try to maintain that accuracy, but now it's just going to slowly drift from that accuracy, but at least now I'm relying on my local stability of my oscillator to say, well, I don't necessarily have to drift very quickly. So it's a nice way of kind of saying, well, I'm going to remember about what my offset is, in terms of frequency, like a parts per billion or parts per million offset, but it allows you to kind of maintain that. And all it is the local component of the local clock becomes your drift component on how well you can maintain that. And for frequency, you can get pretty good accuracies. A lot of times you can get like TCXOs that can get, a lot of times they're around 300 ppb, they're getting down to 100, and even some down to 50 ppb of accuracies. But you can even get components of oven compensated oscillators that you can get into like 10 ppb or even 1 ppb of stability of that drift component. But the thing to be aware of is when you look at time reacts very differently to frequency drift. So a frequency drift might look very linear when you look at it from a graph. So you might say, well, it's very linear, very easy to kind of compensate out. Well, the problem is it's not linear. It's actually very, if you really zoomed in on the component, the average aspect, or what they call aging aspect of it, might look fairly linear, but there's a lot of variation in the crystal or MEMS oscillator itself that you might be able to have to try to compensate for. And so if you actually look at it from a time component, a drift component actually becomes more of an accelerator component when you look at time. Because again, when you're drifting away from your nominal source, which means you're actually accelerating away from it. So it'd almost be like you're stepping on the accelerator. If you keep your foot down, you don't always stay at a constant rate of speed. You actually could be slowly keep increasing your speed, right? And as you keep pressing it, if you try to just keep pressing it and you go downhill, you'd actually start gaining speed. And so what happens is you actually get a very fast accumulation of error of phase and time that it becomes very difficult, that unless you're actually compensating that out, it might be very difficult to hold a time component of error over time versus a frequency. So frequency is a little bit easier because you're talking about ppb, but when you look at ppb and relate it to a phase or time component, ppb is nanosecond per second, right? So that means if I'm 10 ppb, I'm moving in phase about 10 nanoseconds per second, but then that accumulates, because if I move 10, I'm now going to move another 10. So in relationship to the source, I'm actually moving 20 nanoseconds faster away from it. And it just keeps accumulating. So you get this exponential effect of it, which is why you see a t squared time representing that exponential component as you go in time. And so it can be very difficult to maintain if you're using like 100 ppb or even 50 ppb. It's hard to maintain microseconds of time error, even for short periods of time. Like even just minutes or even an hour can be difficult to maintain 1 microsecond. And so you need either additional compensation mechanisms or other components to try to improve that. So as a final component of the servo, let's look at the noise, because that's one aspect that a lot of times gets ignored. Is people look at, a lot of times people will tell you a performance of something and they say, look, when I'm locked to the grandmaster and looked at my error over time, oh, I see my error is only off by 10 nanoseconds, right? but that's under a very ideal condition, right? But the reality is there is no ideal condition when you deploy this into a network. When you start doing network distribution, well, you start accumulating noise over time. You start, there could be rearrangements in the network that redirect timing packets, which means you have to adjust for it, things like that. And so there becomes all this little variation that can occur. And if you look at physical layer clocks, it's the same thing. You could have variations in your attenuation. As temperature changes, the rising edge and falling edges might change. And so you get a lot of noise, what we call high frequency noise onto that clock, which is like the red line. And what you want to try to do is you want to take all that noise out and try to follow the clock as precise as possible, which is the blue line saying, if the clock is drifting, I want to drift with it. I want to follow that clock. And if it's not drifting, then I want to make sure I'm also not drifting in relationship to that clock. And so that's where we're trying to filter out high frequency noises in order to maintain the low frequency traceability to that clock. And so the ITU termed these concepts of jitter and wander. Basically, jitter is very short-term variations, what we call very high frequency noises. So if you looked on a scope, you'd see like a lot of movement of the clock very quickly, right? But wander is what we call low frequency. So it might be moving very quickly, but it might be very slowly moving in time from one spot to another. So that would be the wander aspect of it. And so what you want to do as a servo or phase lock loop is you want to eliminate the jitter to try to get it stable, but you want to still follow the clock itself because that's the clock you're trying to maintain your accuracy to. And so basically the function of the PLL is just that. It's to attenuate jitter, which means filter out all high frequency noise, but transfer the wander. You want to make sure you maintain that traceability. And when you look at frequency, again, frequency a lot of times, you're typically looking at just maintaining like microseconds of phase traceability to that clock, right? Because a lot of times components allowed the ability to do jitter buffers and control that. So that's why you see like a lot of times a phase lock loop in the early days, really what it did is it just basically allowed you just wanted to follow that drift over time, but just attenuate some of the high frequency noises. So if you look at it from a response to injected noise, you can look at it as very simpler as, whatever noise is coming in, you want that noise to come out at a certain point, right? At a certain frequency, you want to say up to this frequency, allow that noise to pass through, but beyond this frequency, I want to eliminate it. So it becomes basically, what we call a pass band, which is all the noise in the very low frequencies will pass through, which means I'm maintaining my synchronization to that clock or my traceability to that clock. But any high frequency noise I want to attenuate so that I don't pass along that noise downstream in the circuit. If you're looking at it from the oscillator standpoint, well, the issue with the phase, well, not an issue with the phase lock loop, but one of the characteristics of a phase lock loop is although the closed circuit is trying to follow the input reference, the problem is any noise variation that happens to your local clock itself actually passes to the output in what we call a high pass filter noise, which means if you have a very quick change of your local oscillator, you're going to see it immediately on the output because there's no way to filter it, right? It's just going to basically go right through. The phase detector will eventually detect it, and the loop filter will eventually try to steer it back to where it's supposed to be. But it basically, the initial aspect of that noise passes through very quickly. And so this is why you have to sometimes find a balance between how long do I want to try to average that noise, like my loop filter, how low do I want to put my bandwidth versus how stable is my local oscillator itself. And so you have to find this fine balance in order to do this. And again, a lot of organizations did this to do this. And a lot of PLL vendors, the silicon timing vendors, can also provide characteristics of that, of how to define your system to say what's the best cutoff to define that. And like I said, you can implement a phase lock loop in software or hardware, but there's some disadvantages when you look at software to a hardware component. So the nice thing about a hardware component is the traceability and the characteristics of how it behaves to noise is a mathematical certainty. There's nothing that can kind of throw it off, right? As you're feeding the noise in, that phase detection is passed to the loop filter immediately. There's no delays. If you correct the clock and have it back to the feedback, you see that response immediately as part of the feedback mechanism. So it's very easy to implement a phase lock loop in hardware and get very precise aspects. When we start looking at software, there's other things you have to look at, because now it's running in software. Well, there's scheduling things that could impact it, right? So the filter might say, hey, I need to do a correction, but that correction may not get down to the hardware until tens, hundreds, and maybe thousands of milliseconds later, depending on certain things. Or the filter itself may not get scheduled in to actually execute the math to start doing things. And so you can get some variation in aspects of that. But even if you have a good PI filter implemented, which, Linux PTP has one, don't get me wrong, it's a very good PI filter. It behaves very well. You can measure it and see that it behaves very similar to a standard loop filter. But there's a couple things you start seeing, right? One is there's a definite gain peaking component to it, and it's very large. It's actually up to 2 dB when I was talking about 0.1 to 0.2. It's almost 10 times as much gain peaking into that circuit than a hardware-based mechanism. And again, you're looking at the cutoff frequency. You could say, well, I could adjust that because we measured it's around 0.4 hertz, 0.5 hertz. Well, yeah, it'd be easy to tune that to get it to the 0.1 hertz or lower. But the gain peaking component becomes a little bit more difficult, because as you can appreciate it, there's a very correlation between how fast you can correct your hardware versus seeing the response to that as well. And if you're too slow, that's where you get that gain peaking component, where you might have started doing an adjustment and then realizing, oops, I've overshot that. By the time you get to react to it, it's too late. You've already overshot it. With a hardware loop filter, you can get a more faster reaction to that to control some of those gain peaking characteristics. So that's why you're starting to see the introduction of hardware-based PLLs starting to get introduced for use in 1588 applications. So very common in telecom, but you're even starting to see it introduced even into the data centers, right? You're seeing PLLs being put down onto NIC cards in order to do some of the filtering. Some of it might be for physical layer clocking, but it actually could be used for packet-based clocking and filtering as well. And so that's kind of some of the things that you can start getting. And now you start getting something that's a little bit easier to control, because a lot of these PLLs allow you to just simply specify your bandwidth and your target gain peaking, and it controls how it programs the PI filter to make sure it meets those aspects of that. So you don't have to be a servo expert to try to say, well, how do I go and program Linux PTP servo to get the same characteristic? So there's some advantages to the hardware-based mechanisms. But there's other things that you can get benefit of. Sorry, that slide got stuck in. The other benefit of getting into hardware clocks is you can start combining characteristics of clocks as well. And you might say, well, why would I want to do that? Well, there's a lot of advantages of doing that, which comes to the whole thing of looking at the noise components of the noise coming in and the noise coming in at the oscillator circuit, right? So if I look at two independently running circuits, I could have, one has a certain noise component and might be running at a certain bandwidth, another one running at another one, right? But if I actually took the output of one and fed it into the oscillator circuit of the other one, what I can do is I can actually create what we call a bandpass filter, which that's actually a very unique way of trying to say, well, I can take certain characteristics of one clock and combine it with the characteristics of another. So I can take characteristics of, let's say, a physical layer synchronization clock, which allows it to run at bandwidths that are much higher because it's working with much higher frequencies. It can basically filter things out and react faster to it. But I could feed that into something that maybe is running a little bit slower because it's a packet base. It's only getting 16 updates per second, or even 1 packet per second. And I could combine that to try to get an overall combined clock that is very stable, right? Much more stable than a local oscillator because it's now traceable to cesium or rubidium clock, but I also still get my traceability to the time source. So I get both accuracy and stability from two different sources and combine them into one. And there's a lot of applications for this, and we see it already today. You see it in telecom when they're doing their primary reference time clocks and now what they call the enhanced primary reference time clocks, where they're trying to combine the benefits of a ultra long-term stability of a cesium to that of traceability to UTC to generate clocks. We see it in the OCP tap time card, we're using these miniature atomic clocks, combining it with a GNSS receiver, and combining that to try to get a good time source clock into the data centers. And we even see it in network distribution protocols, like in telecom, they use it what they call a telecom boundary clock, where they basically take the benefits of physical layer synchronization and packet-based synchronization and combine them together to get an overall clock. And even that concept is used even in concepts of like White Rabbit and things like that, where they're trying to do it. You know, the difference between White Rabbit and a telecom implementation is just the assumptions that had to be made between the clocks. In telecom, the frequency distribution network was well in place long before a packet-based network came in place. So they had to make sure they maintained those two independent sources. So they had to make sure they developed it to do that. For White Rabbit, you can make a lot of assumptions saying, I'm the driver of both the physical layer clock and the time clock. And so you can use that to simplify some of the servo and filtering mechanisms to recover the clock and get those precisions that are discussed as part of the White Rabbit consortium aspects. So, you know, and again, this is just an example of how it's used today in ITU. So it's not a concept, it's actually in place. There's already existing networks that take advantage of this clock combining and uses it. And it's actually could have a lot of advantages in the data centers as well, because you don't necessarily have to follow directly the telecom standards, but you could follow some of the techniques in order to try to do clock distribution. And you could do it both not only network-based clock distribution, but even within the node, server node itself, which I know there's been a lot of presentations if you follow the OCP TAP community on like the precision frequency measurement and other aspects that could be introduced to allow distribution of time between cards. And so with that, I'm going to stop here. I think I've gone a bit over. I apologize, but it's a lot of information, as you can appreciate, to get through. So I'll stop here and see if there's any questions.
Thank you very much, Greg. Wonderful presentation. So let's open the floor for questions. Any questions? Maybe an icebreaker question, Greg. Like when it comes to the PI approach, like for the servos, what do you think? Like, let's say, I mean, alternatives such as like LinReg or like some other smart things where they can get rid of outliers. What do you think overall about those?
Yeah, for sure. You know, like you know, the nice advantage of a PI filter is it's a very simplistic mechanism. But one of the downsides of it is if you don't have, it doesn't do well against non-linear noise, which is why, you know, one of the slides I kind of skipped through there because I didn't really talk about it, but it's a good example is when you look at trying to distribute a packet clock through a network where it's going through a lot of delay variations as it's going through the network and gets to the final node, you could try to apply a linear aspect of filtering to it, but what you find is you get a very large error in terms of your offset to your grandmaster. And it's just because inherently it just could basically shifts that noise up. And as you highlighted, you know, to take advantage of that, that's where things like finding outlier detectors could be used to say, well, what if I ignore packets that were heavily delayed? Or even in terms of, you know, if you don't want to look at packet, even physical layer clocks, you could do stuff like saying, what if I ignored, instead of looking at every edge, maybe I only look at very good edges, right? So maybe I actually filter out certain edges that are very attenuated and ignore them so that it doesn't have a huge influence to the circuit. So definitely you could see the combination of PI filtering with other techniques used. And it's even commonly used in telecom. Like, you know, you hear about the lucky packet. You know, fundamentally, all the lucky packet is doing is trying to find the very least delayed packets going through the network. But fundamentally, all it does with that is pass it to a PI filter. But it's just a PI filter with a very large time component, right? So the idea there is because of that, you need a very ultra stable local oscillator to try to stabilize your clock. Well, that's not going to be very economical if you're trying to create multi-line cards or multi-card devices. You have to find different techniques. So you have to try that. So that's where algorithms come into place and different things. I agree.
One more thing, like I see servos do relatively well, let's say, in the presence of the connection, but they pretty much freeze when you enter holdover. Wouldn't it be good, like, if we had something that let's say was still active, let's say doing some more things? I mean, let's put it this way, like you add a temperature sensor as well to the thing. I mean, often NICs have like you can put, let's say, take the information from the temperature. I mean, it's not necessarily on the thing. You're building like a software TCXO, but I mean, there are other things like perhaps you can model things to. I don't know. What do you think about that?
No, I agree. And definitely you're starting to see that already. You're starting to see, even vendors, not only just silicon timing vendors, but even oscillator vendors, they're trying to find ways to improve the stability of their own clock, right? And so you see people coming out with what they call like GNSS disciplined oscillators, where they say, well, give me access to the GPS when it's available, because I can use that to try to learn aspects of my own error of my own clock and try to fix it so that when we go into error, if I lose GNSS, I can now have better stability because I learned aspects of my crystal or my oscillator itself, right? So that's a very common technique. And you're even seeing it at a system level where you combine the characteristics of a servo with an oscillator, because the advantage of the servo is a servo sees more than one clock, right? And so you could take advantage of that, right? Like just because there maybe is one source has been identified as the best clock or as the highest quality level coming into the system, I have access to other clocks. There's not only one grandmaster out in the network, right? So why not monitor the other grandmasters and see if I can see variations that I can say, well, I can filter that out. So it itself is still a servo component. It's just some people think of servos as, well, it's just a PI filter. Well, that's not entirely true. It's true for physical layer clocks. Typically, you use just simple linear techniques. But when you look at packet-based clocks, or if you're looking at now where people are starting to focus very heavily on, it's not necessarily how well my traceable to the clock is. It's like, how well can I maintain my clock to be a very good clock, right? It's more about, I want my clock to be good, right? And every periodically, I'll measure to make sure I'm still traceable to a good source, so we can make sure I'm relatively at the same error to another node. But my clock itself, I don't want it to move. Why move? Why move 1 nanosecond? I shouldn't have to, right? So I agree. You're starting to see a lot more of these things start being introduced, and they're being introduced not only just at the software layer, but some are even being pushed down into the hardware to do some of this automatic, learning. You could almost call it like an AI concept being added right to the timing silicon itself to improve these servos.
Thank you, Greg. Any more questions? I mean, I've
I
seen
was
the
wondering,
comment.
hi guys.
Yeah, go ahead, go ahead.
Hi, Nazar.
Well, first of all, Greg, congratulations. You managed to include enormous amount of information in 1 hour and deliver it clearly. So that's that's impressive. I envy you. I'm curious about your thoughts on that Linux PTP software implementation. You mentioned that, well, you're having issues with peaking because of the software delays. And obviously, what scared me at that point is, well, if it's software delays, they're not deterministic. So my peaking can actually vary as a system load, for example. So I was wondering, what are your thoughts? Is this just, a flaw or sort of possible room for improvement in the implementation of PTP4L? For example, if you could move filtering the processing part, the servo part, to, let's say, a kernel module to give it a priority to make sure it actually does execute on, let's say we have 64 messages per second or 128. So it does have to execute some actions in those intervals to make the calculation and apply the correction.
For sure. I think your statement is true on both aspects. You could call it a flaw, but I wouldn't say it's a flaw. There's nothing wrong with the implementation of the PI filter. But the flaw is there's probably a handful of people that would even understand how to manipulate the PI filter to do what they want, right? So if you go and say, well, can I improve my gain peaking? Of course, there's aspects that you can improve the aspects of the integrator component to try to say, let's improve it. And as you highlighted, there might be ways of saying, well, could I give some scheduling priority or even push some aspects to the kernel? That is also an option. And an option, that approach we took, is we took the approach of, well, why can't we kind of maybe, instead of doing the filtering in software, push it down to hardware? And so that is something that we've started, and you're starting to see more silicon providers open this up, is there's no reason why you can't just pass the phase offset directly to the hardware and say, you do the filtering. And then I have the feedback through other mechanisms, because it's clocking the timestamp or other things. You can still use the clock as you did normally. So you still get this aspect, but now the filtering is actually pushed to hardware, and you're having more of this controlled response, or a very mathematical certainty of the response of how it's going to behave in terms of that. And some of the advantages is some of this hardware actually has capability to detect that if there is a huge delay in getting that offset down to the hardware, well, it could put itself into holdover and say, well, I'm not going to steer myself to the last offset that was given to me, because that's now stale. So I'm going to ignore it and start stabilizing the clock to say, maybe there's an issue. Maybe software lost its connectivity to the NIC card. So instead of relying on that, it basically allows it to automatically hold the clock and do stuff like that. So I think what you're going to see more is probably more of this coordinated effort, right? Where you start maybe pushing some aspects of it to the hardware that is more, the simple compute stuff to the hardware, that if it's available to do it. The more advanced stuff, like maybe your outlier detector that you may have, or some other algorithm to try to predict or detect, you maybe have that still in software, because that's not as devastating to delays, right? If you're trying to predict, you're not as devastated to say, well, I was late to do the update, right? Because you're still trying to predict. If your prediction isn't ready to update, well, it's still running, right? So there's aspects of that stuff could still be in software.
Mhm,
All right.
understood. And
Any
if
more
you
questions?
are,
Sorry, go ahead.
Okay.
so if you're running the PI servo, basically the control loop in the hardware, is some sort of a model of that servo available to the user? So for example, a user could understand how to analyze stability of the loop when they are choosing the PNI coefficients.
I would say yes. And as I highlighted, majority of silicon vendors have implemented the what they call the Type 2 PLL. And so because it's a second order concept, a lot of that modeling of second order concepts is heavily used in the industry to model network behaviors itself. So when you look at the ITU-T, when they try to say, well, here's the network model we want to use, and here's the network limits that would be imposed, a lot of that is because they can model the behavior of these second order filters much easier, because it's a more of a known mathematical certainty of how it's going to respond. And so that's kind of one of the advantages. So that's why what they do is they push down, saying very specifically, like, you must operate it maybe within this bandwidth range, right? Like Sync-E, it says you must operate between 1 hertz and 3 hertz, right? For PTP, it says it must be between 0.05 hertz and 0.1 hertz, right? So they basically rely on saying, well, if I tell you the range to operate in, I expect you're operating in that range, so now I can simulate the effects of how it's going to happen in the network. So the modeling is kind of already there, I would say, because Type 2 PLLs have been well used in the industry for a long time. Where you're going to get difficulty is if you're looking at stuff that is doing more of an adaptive approach or an outlier filtering approach, because it's much harder to model that, because it's very dependent on conditions, like how good the signal is coming in or the packets coming in, and things like that, and aspects of that. But what you can maybe model is saying, you can impose maybe a minimum expectations. Like, I expect to at least get 2 good packets within a 100-second interval, so that I can overall maintain a certain level of traceability to that clock. So you can maybe start modeling some aspects of that to try to put limits on, saying, well, if I know I'm going to get at least 2 packets in 100 seconds, then you could kind of translate that to what a linear model of that would be. if you only got that many edges in that interval, right? You could say, well, that would be similar to a BLA filter and model what sort of behavior you would get out of that. It's not perfect, but it's a way to try to bring it back into a linear aspect concept.
Makes sense. Thank you.
Any more questions?
Yeah, Greg, one more question from my side.
Sure.
Is like how the hardware filters are helping in the PTS side. So like we don't have Syncy in that scenario, how the hardware filters will improve the synchronization.
Well, so like one of the nice things of the hardware filters, and especially some of the nice things of some of the bandwidths that the ITU even picked. So the ITU did a lot of work on here to try to identify ideal filtering aspects for PTP and Syncy, and then they also modeled, well, what happens if you have Syncy, and how does that noise inherently transition onto the PTP output. But the nice thing about running at 0.1 hertz is 0.1 hertz was actually, as a bandwidth, was actually used in telecom in North America for Stratum 3, for sonnet level synchronization. So, and with that, people already kind of know kind of the noise model of using a 0.1 hertz bandwidth and what sort of stability you need for an oscillator. And typically, these 300 ppb stability TCXOs can help us, are stable enough that it allows you to run at that 0.1 hertz bandwidth and still synthesize a very clean clock coming out of it. You know, it won't be as good as having the physical layer assistance. You know, with the physical layer assistance, and I didn't talk about a lot of the measurement techniques, but if you look at the time deviation or TDEV component, which kind of tells you about how stable or how well your clock is, you know, you're typically trying to target like sub 1 to 2 nanoseconds when you're looking at with physical layer assistance. You know, when you add, you know, get rid of that, you still probably could get in upwards of maybe 4 to 10 nanoseconds of stability on that. So it's still a fairly stable clock that you could use. And so, you know, there is aspects that you could still use these hardware servos still to even filter, you know, if you don't have the physical layer assistance, and you can get very good stability with this. And again, you still get that control of the gain peaking with that aspect as well.
Thanks for the explanation.
Any more questions?
Yeah, Greg, I had a kind of a standards-based question. So you kind of hinted at it in your presentation about like combining clocks. Is there any kind of like standard mechanism or servo description of like clock quorums to generate what I think they're commonly called like paper clocks? Like you have 10 atomic clocks and your output clock is not necessarily traceable to one, but traceable to all. And you don't even necessarily discipline any of them. You just kind of generate a synthetic output. And so I'm curious, like, how is that commonly defined? And then also what kind of hardware mechanisms are used or available or not used to generate that kind of function?
Yeah, I would say there's not a common, you know, I don't think there's one place you could point to do that. Now, there's definitely work being done around that. The ITUT is doing it as part of their, they have a primary reference time clock. They're calling the coordinated network time clock. And they're also looking at aspects of having, like, what if you have more than one cesium source available? How do you take advantage of the two or more type of thing and combining them to get frequency sources? So there are, I would say, discussions looking at it, but to say that there's right now somewhere where you can point to say, here's a common way to do it or a recommended way to do it, I'm not sure if there's anything quite ready yet for that. But a lot of times, you know, you see the practice being done elsewhere. It just may not be called the same thing. Like I know I've seen, like, if you look at Smart Grid and Power Grid, they do some fancy things looking at the phase relationship of multi signals. So they call it almost like a multi-input phase lock loop, where it's actually it's combining, kind of like what you said. It's looking at all the sources and it's kind of dynamically weighting them to decide which one that it uses and which one does it try to heavily weights it, or maybe they're equally weighted. And if there's something detected as being not quite good, it could actually eliminate it from being included. And they were starting to look at some of those aspects as part of their fault redundancy or fault detection and stuff like that. So I think it's coming, but I agree it's not something that I could just hand you a paper or something to say, here's how you do it. But there's definitely devices out there that can help you do it if you want to come up with your own ways, which, I know the OCP the TAP group has looked at different ways of doing things like that by looking at clocks for distribution.
Okay, great. Thank you.
I do have a question. I'm curious how the data centers nowadays bring in the most precise clock. Does it brings in from like a GPS receiver through the time card, or there's other way they bring the accurate time to the data center?
Well, I could give my opinion on that, but sure, Hamad probably way better at that. But
No problem.
I would say the
go
time card is one of the mechanisms they're looking at for sure. Like today, I would say a lot of it is probably more of a, almost like an industry specific. Every operator out there may have had their own way of how they're starting to do it, right? Some were buying maybe unique server boxes that had capabilities of bringing GPS in. Some were looking at for addressing Open RAN and trying to look at solutions. So they were creating like new NIC cards that maybe had capabilities and even integrating GNSS receivers into there. Some were looking at expanding to look at the telecom, so even supporting concepts like SyncE into the NIC card itself to actually take the recovered clock component and use it to stabilize the local clock. And then you have also areas that they're looking at for trying to distribute that within the server box itself, right? So you have the precision time measurement that's being looked at, and there's been a lot of discussions on that from I think Kevin from Intel or prior Intel gave talks on that, and things like that, to how to distribute that information now within the system. And then there's even people looking at ways of doing, looking at ways of trying to say, well, that's one way to do it, but it's maybe there's a lot of variation or noise in that. Is there a way we can stabilize it by looking at ideas of what we call a common clock, which is kind of back to that pleidiosynchronous thing that I kind of introduced way earlier in my presentation. But that's where you can maybe look at relationship of two clocks at one area and the relationship at another one, and try to use that to try to pass frequency information between two cards within that as well. And Julian's called that the precision frequency measurement concept as well. He's introduced through the talk here as well. So I don't know if I quite answered your question, but I would say it's still new. It's not like I would say it's not a short answer of saying it's done this way.
Do people typically deploy the time card for syncing the GPS timing? Do they deploy it on the gateway, or mostly just deploy in the server, or both?
Well, that honestly would probably be very much an operator related question, because I think everyone will have their own idea of the best way to do that. So, the idea of the time card was to kind of bring time into the server. But there's definitely ways you can use time cards to distribute. So you could do like distribute between systems using the time card. You definitely could have, and even the data center, even the OCP TAP has created its own 1588 profile to talk about how to distribute using a time distribution protocol to distribute time throughout it, through the spines into the top of rack and into the servers as well. So, I think all the approaches are being looked at for doing it. And again, I would say there's no one common way. It's really going to be the operator or the data center manager is going to determine how they want to get time into it, or it could be how they want to even provide it as a service. as timing as a service may dictate how they do that type of deployment scenario. And Ahmad, feel free to step in.
No, I mean, you definitely addressed it very well. Yeah. So like Eric, basically, there is no size fits all. But let's say if you're speaking like overall, let's say economics comes in. I mean, you can have the best clock in the world, but you can be wrong. So time dissemination is very important. So you have to, like, basically what time card does is it brings the time for, let's say, I mean, in this common architecture, server is basically known as grandmaster. And then the rest is time dissemination to cheaper oscillators, like you have XOs that are on the server, on the clients, and then the clients, yeah. And so instead of, let's say, putting a time card can have a miniaturized atomic clock. It's not cheap. You don't want to put that in, let's say, hundreds of thousands. So you keep things as they are, and then you rely on the dissemination, and then it works. But let's say you end up with a cluster that is doing, let's say, I don't know, just for example, it's AI, and you have to, let's say, I don't know, measure current propagation, and you have to, like, TDM things and avoid, like, so for those, you make a raft, and then that raft can go like higher, like the servos will run much, much faster with like one central node as like a, let's say, representative. Central node gets the same one, like once per second, but the rest, they will basically use that one. So you can go completely asymmetric and solve the problem. So that's what we basically did with the like the PTP profile. We just broke all these, like, let's say, not broke, I mean, we tried to figure out, liberate, let's say, all those constraints, as long as they really don't make that much of an effect, let's say, in our case, and keep them optional, so then you can choose how you want to modify things based on what you have. So I hope that answers your question, Eric.
No, you did. Yeah, thank you.
So any more questions? I mean, wow, we are almost half an hour above the hour. Great. So if hearing none, we'll adjourn, and we'll see you guys in 2 weeks, where Roll from Fugro will talk to us about the technique they're using that augments basically GNSS signal to get us to sub-nanosecond. Right? So we'll see you guys in 2 weeks.
Thank you.
Bye,
Great
everyone.
presentation. Thank you. Bye-bye.